G&W Electric's legacy started over a century ago. Since then, we've continued to find new ways to revolutionize the distribution of power on the grid. We are the innovators that drive our communities forward every day by playing a critical role in providing you with reliable, innovative solutions. We're a leader in engineering and building advanced products to keep power flowing around the world. We started with the first disconnecting porcelain pothead and developed the world's first high-voltage pole-top recloser, the Viper HV. And we've energized a world-class 2-megawatt microgrid that powers our headquarters with a combination of solar power, a flow battery, a diesel generator, and an amazing flywheel for instantaneous backup in our molding operation. We're developing solutions to enable the transition to the grid of the future. Renewables will drive the need for more switching, sensing, fault protection, and intelligent systems throughout distribution and transmission networks. We listen to understand your challenges, and we engineer solutions that meet your needs for the future. We understand that equipment must be automation ready and developed with modularity and flexibility in mind. We know applications require more robust, sealed construction with fewer components to operate longer in hotter and more extreme environmental conditions. And they must have sensing capabilities that allow them to monitor critical data for optimizing power delivery and reliability. As we look to the future, we embrace the 3 Ds: digitalization, decarbonization, and decentralization with increased capability. Here at G&W Electric, we're laying the groundwork for more resilient, smarter cities, creating greater efficiencies, and engineering the next evolution of power.
Good afternoon, everyone, and welcome to the Enlit Asia Digital Series. Thank you for joining us today for our webinar session titled High Accuracy Sensors for Tomorrow's Energy Grid, hosted by G&W Electric. We are very pleased to have Michael Buress, Global Product Manager for Sensors, with us today. He will be sharing insights into the latest trends and best practices shaping the future of energy grids. Now, ladies and gentlemen, we encourage you to actively participate and ask questions along the way. Without further ado, let's welcome our speaker, Michael, and over to you.
Hello, everyone. Good morning, good afternoon. Today, we are going to talk about a very interesting topic, high accuracy sensors for tomorrow's energy grid. So, my name is Michal Bureš. I work as a Global Product Manager for Sensors in G&W Electric, and thank you once again for joining this presentation. I hope you will enjoy it. So, let's start with the question, what is tomorrow's energy grid? So, to answer this question, we need to look at the situation of the most existing grids around the world today. The majority of grids are centralized, usually designed around one stable generation source with one-way power flow. Usually the penetration of distributed energy resources, we will call them DERs for today, is still very limited. Such a topology has been in the past enough, but for the standard protection scheme with straightforward voltage control will definitely not be enough due to growing demand and implementation of all these DERs. Plus, the time expectation of fault restoration is more and more crucial due to penalties in some countries. So, the future grid requires more measurement and, of course, more sensors. DERs are coming, the grid will become more and more diversified and will require more monitoring and more automation than before. So, the power flow, So the power flow is not one way only, right? But thanks to the microgrids, Icelandic and active role of customers, the two-way power flow will be a standard in the future. The future grid also consists of more power electronics, more inventors in the grid, and of course, what are the consequences of the implementation of these electronic devices, we will check later in this presentation. So we can understand that these changes are very significant, and definitely no one's want to change the grid layout completely in the country, in the region. So for this reason, we need to do three things. We need to harden the grid, we need to smarten the grid, and we need to grid greener. So does it sound familiar to you? Then probably you are right. There is a way how to adapt and how to make the grid more resilient. I present to you right now the 3Ds. So the way how to make grid more resilient and how to challenge the opportunities. So particularly the 3Ds represent decarbonization, decentralization, and digitalization. Of course, the carbonization consists of renewables as implementation of the photovoltaics, wind turbines, hydropower plants, battery storages, and so on. Plus, it applies the regulation on the reduced power losses, as especially for the power transformers and the distribution transformers. This activity is already ongoing. I would say not all around the world, but regionally it's already ongoing. And of course, it always depends on the local authorities and regional strategies. The second pillar is decentralization. So it represents implementation of the microgrids, DERs, and hardening the grid in general. And finally, we have a digitalization, which stands for implementation of the measurement, specifically sensor, more automation, the asset management, and the digital twinning. Okay, someone can say that the trend is not that rapid. We don't need anything of that. We don't need 3D, we don't need 2D. Our grid is resilient enough, but let me show you something. I have done research by myself, and I was quite surprised how the trends from the last decade, and maybe not even the last decade, but maybe just a couple of years ago, changing the electricity consumption. So let's start from the bottom. Almost everybody uses the smartphone, right? Plus, majority of smartphone users use also wearable devices like smartwatches, Bluetooth headphones, tablets. Now I have seen also the smart rings for the payments. So the number of these devices is roughly 8 billion worldwide. And to charge all these devices, we need annually 25 terawatt hours of electricity. Second, EV charging. So it's a very fast growing industry. Right now, roughly about 40 million electric vehicles all around the world. And of course, to charge these vehicles, and let's consider some average consumption, we need 100 terawatt hours of electricity. Of course, this number can be double, maybe triple in a couple of years as the industry is rapidly growing. And the last one, but probably the most important one, data centers. So right now we have approximately 10,000 data centers all around the world. And these data centers combined consume around 460 terawatt hours per year. The prediction is more than double in 5 years. So 1,000 terawatt hours in 2030. And it is expected that, for example, in the United States, the electricity consumption just for the data center will be 10% of the whole production. So if we combine these three new trends, so we have annual consumption of almost 600 terawatts per year. So for example, you can see the France electricity production was 527 terawatts this year, so lower than required. Okay, these numbers are crazy. We have technology right now what was even not considered decades ago when the grid has been planned, and we can just assume what will happen in the following years. So to be able to handle this transition, to fulfill the market requirements, the concept of smart grid was presented years ago, and it looks like it was pretty accurate in that time, and we are closer and closer to the prediction. So smart grid involves all the stages from the generation to the customer. And to go one by one, let's start with a production on the left side. So the production in the future will be more diversified with numerous small-scale power producers. This trend is already happening. We can see it almost everywhere. Very similar with the market. because the market will be not centralized, not respecting the borders, not everywhere, okay, but in most of the places. And for example, this trend is already happening in Europe and the other regions. Same with transmission, it will also change in the future. For the short distances, we can expect some level of scaling also, with definitely support of the battery storages. And for the long distances, we see trend with ultra high voltage transmission lines for both AC and DC. Regarding the distribution level, as I already mentioned, the two-way power flow is almost must, and one of the reasons are the customers, because customers are no longer just the passive users. Now they are like active participants because they have their own power plants, photovoltaics power plants, wind turbines. Also, they have battery storages, and also they are using electric vehicles. So many of them are prosumers now. So to wrap up this futuristic section, let's go back to the DERs. So we can agree that they are not going away. The impact of the DERs will grow, and our goal is to implement them properly. So every coin has two sides. So there is one challenge I want to highlight today. It's about the power quality. And I would like to ask you to answer for yourself following questions. So what are the impacts of the DERs on the power quality? How do you want to manage this impact? And also, how do you want to measure this impact? So maybe I can help you with the answer. So let's check why we need high accuracy measurement. If I would like to explain the role of the sensors to my best friend who know nothing about the electricity, I would say that the sensors providing the better view of the grid. Sensors are the eyes and ears of the grid, and high accuracy sensors can see what we are not able to. Our customers want information about the grid behavior at touch of the button. They don't want to wait for some results, for some reports. They just want to see what is happening in the grid. So our common goal is to provide the voltage stability, increase capacity, and efficient power flow. We are saying that at least 0.5% accuracy is mandatory today to be able to properly see what is happening in the grid. Of course, the accuracy can be provided also by traditional instrument transformers. But there is one thing, traditional instrument transformers provide, as we are saying, restricted visibility to the grid. So not showing the hidden secrets. On the other hand, we have sensors, and sensors can provide unrestricted access to the hidden secrets. And what are the hidden secrets? It's about the harmonics. So higher harmonics can create a huge power quality issues, and it can be very difficult to measure them with conventional solutions. Good for us. We can measure them with our Accusense sensors and solve the issues. We can see that our customer investing a lot into digitalization to store the data. They are making the models on historical trends, predicting the failures. So there is a way how to deal with it. But again, the accuracy measurement is required. So let's check the other drivers which are evolving the grid. First, as I already mentioned, it's about the power quality programs. So we have a power quality measurement, volt valve control, CVR. Again, we have also some grid modernization because the infrastructure is aging. So we need to replace them with a modern solution. We need to improve the reliability and resiliency. In some of the cases, as I already mentioned, classical CTs, VTs are not enough because of measurement, for example, of the low currents, where the utility could probably bill the customer, so we can provide the visibility of the low currents. And then we have like these analytics condition assessment, so asset management, predictive analysis, preventive maintenance options, frequency range measurement of superharmonics, which is one of the topics we will, let's say, discover later in this presentation in our use case. We can, let's say, achieve some great results, I would say, with fault locations. And of course, thanks to sensor, we can have fast fault detection, and thanks to the grid visibility, of course. So there is one last question mark of the future grid is following. So there is one trend growing more than others. It's the AI. Of course, it's a tool that becomes more and more implemented to everyday life. By the way, this picture was also generated by AI. And at this moment, it's very difficult to predict the impact. If AI will play some significant role in a grid automation and so on. But my personal opinion is that the impact will grow for sure in years. And it's just up to us how we will handle this trend. Because one of the most important thing for the AI and for the machine learning is about the data. Yeah, so the future grid is all about the data. Data represents information, and the information, of course, is only valuable if it is accurate. This is why we are saying the high accuracy sensors and high accuracy measurement in general is super important these days. So if we all believe that, the machine learning, automation, data analysis, predictive analysis can play, and also predictive maintenance, for example, which can save a lot of let's say cost for the utilities. So if all these, let's say, roles can play some important role in the future, we need to provide the models with very accurate data. How we can do it? It's thanks to high accuracy sensors, of course. And as I wrote down here below, so the worst thing we can do is rely on inaccurate data and let them influence our decision. Okay, so let's leave the world of the future for now and let's go back to reality. So let's check the sensor technology. First, we need to understand that sensors are enablers. It enabling proactive grid monitoring, and it is not just a component, but it is a device enabling us to extend the functionalities and providing us with great visibility of the grid. So how we can describe this technology? So we can say it's the next step in the evolution of primary measurement devices, right? The technology is very well known. It has a lot of advantages. We have large global installed base, so we have experience. There are benefits in each step of project and wall life cycle. It's a basic pillar, as we have seen, for the smart grid and digitalization. The output signal is linear, which brings a lot of benefits. We will discuss it later on. And of course, the compatibility with third-party IIDs is there, so this is not an issue. All around the world, there are different, let's say, approaches. There are different technologies. We can just mention the most famous one. So for the voltage measurement, we can use capacitive dividers, resistive dividers, or optical sensors. And for the current measurement, the most common are Rogowski coils, resistive shunts, and Hall effect transducers. So talking about G&W Electric portfolio, so we are using the capacitive dividers for the voltage sensors. We are using Rogowski coil for the current sensors. Also, we are using active and passive sensors. So this is like one of the biggest difference between us and our competitors, that we are using both of these approaches. So we are, let's say, taking advantage of benefits from both the worlds. So the active, so there is electronic inside, so you can adapt the sensor output. You don't need the calibration coefficient or whatever. And for the passive, so there is no electronic inside. You don't need the supply voltage. So what are the key features? So high accuracy up to class 0.5. With active sensors, we can achieve even higher values, like in fact lower values, so 0.2 and so on. There is huge frequency measurement bandwidth, especially for the active sensors and capacitive one. We will talk about it later. It's safety solution, right? So it's absolutely safety for the maintenance and installation. You have metering and protection in one device, and it has high immunity. and like against electronic noise and whatever. Our sensors, as I mentioned, based on the capacitive dividers. So the output voltage is linearly proportional to the input voltage, so it's simply divider. The primary and secondary circuits are galvanically separated. Accuracy class for the standard portfolio is 0.5. It complies with the newest ISC standard, and we are part of the ISC committee. So we are working also on the new standard, which will be released in the following years. You have, as I mentioned, combined accuracy class for metering and protection, so you can measure both at the same time. You can achieve the small sizes, which are ideal for the bushings. Thanks to the capacitive divider, you have high accuracy and temperature range from -40 degrees of Celsius to +65 degrees of Celsius. And as I mentioned, you have a higher frequency measurement bandwidth compared to the resistive dividers. Current sensors, as I mentioned, based on the Rogowski-Kohl principle, it's, I would say, one of the most common solution around the market. The output voltage is proportional to the derivation of the primary current. So yeah, correct. The output of the current sensor is voltage. It also complies with the newest ISC standard. You have again, as for the voltage sensors, combined accuracy class for the metering and protection, so you can do both measurement at once. 0.5S accuracy class, and you have no iron core inside. Also, it allows you to measure, thanks to the, let's say, lack of the iron core, it allows you to measure very low currents from 1 amp, let's say, to the fault currents, like a short circuit thermal currents, 31.5 thousand amps. As I mentioned, one of the main advantages of the sensor compared to conventional instrument transformer is linearity, because there is no iron core, and no iron core means no saturation, and no saturation means linearity of the output signal. So exactly what you see in the output, you will see on the output. So it's very, very efficient. So if we just go through the features very quickly and compare CTs, VTs, or CT-PTs with a sensor. So the signal in this case is very low. It's like 150 millivolts for the current outputs and 2 volts for the voltage outputs. Secondary cable is already included in the sensor, so need to do some additional work. As I mentioned, there is a linearity, there is no saturation. Also, ferroresonance, there is no ferroresonance for the VTs and voltage sensor, of course. So no need to do some the measurement and corrective measurements for that. The temperature coefficients are already included in the accuracy. It's shielded. Also, you can short circuit or open the secondary, and it will be safe. No destruction is happening. It's also much lighter solution if we are comparing the weight, and there is wide, let's say, standardization. So you can, let's say, do like interconnection between different sensor manufacturer and, for example, IID manufacturer, thanks to the standardization. Okay, so as I mentioned, we are using both active and passive, but we believe the active technology is the future, and this is the one what we are pushing, to be honest. So let's spend a couple of slides comparing active and passive sensors. So first of all, the difference is in the correction factors. It's very important for the users because in case of passive sensor, you need to implement the correction factors into the IED to achieve the accuracy, which is guaranteed by the sensor. Each sensor has own correction factor, so it is important to let's say enter it properly into the IED, because if you, let's say, switch the sensors, then you will not achieve the accuracy simply. In case of the active sensor, there is no need of the correction factor. It is already calibrated from the factory, and it is what we can call like a plug and play solution, that really the user just plug the sensors and there is no need to some on-site calibration or whatever. So real plug and play solution. The other thing which is different, we are comparing active and passive sensor, is temperature compensation. The critical point is to keep the accuracy at the same level, no matter how the environmental temperature is. So in the chart, you can see the difference between active and passive sensor, where we see linearity over the wall range for the active sensor, thanks to the, let's say, electronic inside. And the blue one is non-compensated, the passive one. So you can see that the accuracy and the ratio error can be different with different temperatures. Other aspect, what is very important also for the customer is cable length. With passive sensor, you have usually limitation. The secondary cable is usually up to 10 meters. But with active, it's completely different world. So you can go even up to 100 meters and the accuracy is still there. Yeah, it is still the same as we can see in the chart. Thanks to the electronic, the sensor, of course, is also all immune to the changes of the burden, what can happen in the secondary cable with some additional capacitance, if some terminal box is connected or whatever, it can make a mess in the accuracy, of course. The last, but I would say maybe the most important one is about the bandwidth. So as you can see in the chart, active sensor provides much higher frequency measurement, let's say bandwidth, with losing the accuracy. So it's perfect solution for measurement the harmonics and superharmonics. This is the topic what we are discussing also today. Plus, as we are using the capacitive dividers, which provides much better frequency response even without the electronics. So combination, this is what you can, let's say, remember, maybe make some note. So the combination of the capacitive divider plus the active sensor is probably the best variant available on the market for the high frequency measurement, for detection of the superharmonics and for the power quality measurement. Okay. So now you are wondering, so are the active sensors really that great? The answer is yes. But also the passive sensor can provide great results. This is, by the way, the reason why we have as a G&W Electric in the portfolio also the passive sensors, because for some basic measurement it can be enough. But considering the great changes and requirements for the accuracy, we believe that the active sensors are the future. So let's very quickly summarize the key benefits of the sensors in general. Now, it doesn't matter if it is passive, active, it is capacitive, resistive. We are comparing to the, let's say, conventional CTs and VTs. So you have high level of system security because there is no saturation, no risk of error resonance. The sensor is a very safe solution because the output signal is very low, so it's safe for the persons. It is small size, low weight, so you don't need to lift heavy weights. The secondary circuits for both current and voltage sensor can be left open or short circuited. Very fast, let's say, design process. So it is standardized, as I mentioned. The standard describes you what should be the output voltage, what should be the burden. So it can, let's say, cover one design can cover a wide range of the application. Also, the economy of scale, if you think about, so there is much more easier to order the sensor than the conventional CT/VT. So you don't need to clarify the parameters like the burden, like the output or whatever. It is already standardized and works perfectly with ID. Also, for our distributors, it is perfect solution as the delivery is super fast because you can have it simply on stock. And also, it is ecologic solution. There is low level of power losses thanks to missing iron core, and the product is lighter, which means the transportation can be cheaper, for example. So I probably already mentioned this topic many times, and I believe you also heard about it. But let's take a look on high frequency measurement. So talking about high frequency measurement, we need to start with a power quality. Because same as water or air pollution, electricity pollution exists. And this pollution leads to power quality issues. The pollution is caused mainly by modern electronics, inverters on photovoltaics, frequency converters, power electronics with fast switching frequencies like we have for electric vehicles charging. And of course, this problem grows with DERs. So more DERs, the bigger the problem is. But no one is saying that we need to stop with implementation with DRs. It's very important to keep going. No, we just need a better visibility. So what are the consequences of this pollution? So we have like a system failures, losses, inefficiency, of course, higher maintenance costs, reduced lifetime, and so on. So this all leads to cost increase. So if we take a closer look, we already identified that probably the most or the biggest troublemakers are the photovoltaic inverters, EV chargers, and I would also add the wind turbines also, which we will see in the use case in the end of the presentation. So the biggest problem in general are the harmonics, distortions, and high frequencies. Specifically, we are talking about the supraharmonics over 2 kilohertz, which are the real problem these days. So what are the issues? Just to repeat, we can have increased losses in the network. We can have increased thermal stress in connected equipment, in transformers and motors, which is reducing the lifetime, and this equipment is very expensive. We can have incorrect measurement on the control units, which can cause the relay misoperation, which is critical if there is some fault in the grid, which can, let's say, harm the persons or do something on environment. We can have like the electronics malfunctions and the failures, and it can interference with other electronic, which is also not what we would like to see in the grid. But don't worry, there is always a solution. As we already know, the combination of capacitive dividers and the active sensor can do great things. One of the things is the power quality measurement. So where we can measure precisely the supraharmonic signals. The portfolio, what we can see on the left is just a portion of the portfolio. But this specific one we already use for high frequency measurement. The voltage level is up to 38 kV. The standard accuracy up to 0.5. As I said, we can go even into the more precise ranges. The range for the frequency is up to 3.5 megahertz for the voltage sensors and up to 30 kilohertz for the current sensors. So using these high frequency sensors for the power quality measurement allows us to precisely measure the supraharmonic signals. And of course, thanks to this, we can reduce the grid operation cost. Additionally, there is like one more thing. Thanks to the high frequency measurement, we can do very precise fault location because we have, let's say, high sampling frequency. We can compare time versus traveling way and locate the fault more precisely. So then if we have some fault in the grid, we can locate it very fast and we can repair the line very fast. So it's something what utilities definitely needs. So let's check the portfolio right now. So basically we can split the portfolio into two groups, outdoor and indoor sensors, as you can see on the screen. On the left side, you have the outdoor sensor, on the right side, the indoor sensors. You can easily recognize it by color, of course, because the outdoor sensor has additional, let's say, layer coat of a silicon to better perform in the outdoor conditions, of course. All of them are using the capacitive dividers and the Rogowski coils. Plus, we have, as I already mentioned, active and passive variants almost for each sensor, almost. For outdoor, we have, you can see it, we have the voltage-only solution and combined solution. It can be integrated to the overheads. It can be like a standalone unit. It can be connected to the power quality measurement, to the protection devices. Then it's just about the application. For indoor, it is almost the same. So we have separately voltage and current sensors and combined. Also, we are constantly developing, thanks to our own R&D, the new devices for example, the new one, underground AcuSense, can be also immersed with water and simply performs the same. So as I mentioned, we have like a standalone units which can be installed on the overheads. We can standalone units which can be installed for the air insulated switchgear, gas insulated switchgears. For example, you can see the VS24BP, it's a backplug for the cable connector, same as a underground AccuSense. We have the smart bushing, which is perfect for the gas insulated switchgear and can replace the standard bushing, so you can have the same device but with the smart functions. Plus, we have like a smart terminations, amazing solution, so you can integrate directly into the cable the smart function, so you can measure current and voltage in the same time. This is amazing. So with our sensors, as I mentioned, you have metering and protection in one body, so you can connect to the protection relay, you can connect it to the energy meter, to the power quality analyzer, even advanced, right? So most common applications are for the power quality and metering. It's volt var optimization, measurement of the DRs, as I mentioned, the harmonics, and of course, high accuracy measurement. We can use it for the fault detection. We can use it for the under/over voltage detection, loss of voltage, and under and over frequency measurement. Here we have a couple of examples where the sensors can be installed. So just for you, the better image to better imagine the typical installation. So for outdoor sensors, I should definitely mention the recloser solution, then the cap banks controls for the indoor GIS smart bushing installation to the GIS for the switchgear for ring main units. And we have already the SF6 solution. We have backplugs also for the cable connectors. And then for the air insulated switchgear, we have standalone sensors. Of course, the one thing is to precisely measure the voltage and current, but the second thing is to deliver the signal and the information to some proper IAD. So these are the main IAD groups connected to the sensor, or what can be connected to the sensors. Of course, we have protection relays, we have power quality meters, fault passage indicators, metering units. These are most common. There is much more. As you can see, our strategy is not to be focused on one IAD producer, one IAD brand. We want to keep this freedom for the customers. Yeah, so the customers can select based on the region, based on the relations, and so on. So if they like SCL relays, they can use it. If they like any others, they can use it. Just the point is, there is one point. We should know it in advance. I already mentioned that the standard is existing, but the standard also gives you some kind of freedom. So the producers are using different burdens, for example. So we have these different variants in our portfolio to secure the compatibility with different IDs. Let's spend a minute talking about the retrofitting, and then we should check the use case. So I can tell you that sensors are probably the best solution for the retrofitting. Personally, I really like it. It's amazing, let's say, part of the industry, part of the business, because you can easily upgrade the existing installation to a completely new level. So you can use the existing switchgear, you can use the existing layout, you just install the sensors and you will receive, let's say, other monitoring and protection functions. So as I mentioned, all switchgear can be digitalized. It's just a matter of time. So there are probably no obstacles. So how is it possible? Of course, you need to have like suitable portfolio of sensors for both air insulated and gas insulated switchgear, where the sensors can be installed even on site. So this is step number one, and we can see some options on the screen. So we have a solution for the air insulated switchgear. So it's a combined voltage and sensors, combined current and voltage sensor CVS, and then a voltage sensor VS for the air insulated switchgear, and the same for the gas insulated switchgear. So we can use, it is better to use smart bushing for the new installation, and then the backplugs for the existing one for the retrofitting. So the second, let's say, step, you need to have a compatibility with the IDs, with the new one and also the old one. This is important because and in our case, what I'm presenting right now, so especially for the gas insulating switchgear, it is very simple. because we have the solution which we call a correction-free solution, even for the passive. So there is, in this case, there is no need of the correction factor for the passive sensors. This is our invention. We invented this solution, so you don't need to enter correction factors for the passive sensors, and specifically for these backpacks. So example, you can have old ID which is not supporting the correction factors, so you can use the sensors. But if you have even older ID which doesn't even support the sensors input, and let's say accepting only the VTs, PTs input. So we have a package with amplifier which can be seen on the screen, providing signal in the range of 100 to 120 volts. So it is very easy then to connect it to the ID, even this sensor solution. For outdoor application, it's even easier because we just use the existing poles, or installation, which are already there. And we are also saving space and weight, as I already mentioned. So why do we want to upgrade the existing application? So what are the reasons? So for example, we need a volt var solution, and which requires high accuracy voltage sensing. We want a visibility at the end of the line, which can be provided very easily by sensors. We want to measure the power quality and harmonics because somewhere in the grid is the new photovoltaic farm or wind turbines. And maybe we are the utility which has a problem that is not able to detect low currents, with traditional CTs and VTs. So the sensors are the solution what can help us. So as I promised, in the end of the presentation, I prepared the use case. So let's talk about this use case, which is the last part. So our case, as you probably realized during the presentation, is about the power quality observation in a microgrid. So below is a simplified scheme of the microgrid testbed network. So we can see there also the G&W sensing technology location. So what is in the grid, in the microgrid? So we have natural gas generators, we have wind turbines, some battery storage, couple of photovoltaic plants, and of course a load. So this microgrid is serving 200 residential and small commercial customers. So it is real microgrid. It's not a simulation, right? This is not, let's say, unreal. This is real operational grid with real issues. So what we did, we would like to measure super harmonics in the DERs. The goal was to simulate the condition in a grid with DERs and understand the power quality phenomena. For the measurement and data analysis and the connection, we use our AccuSense sensing technology, the voltage sensor. We have 0.5 accuracy class and the power quality analyzer. As we already know, super harmonics have the potential to disrupt network operation by damaging capacitors, degrading the electric insulation, and misoperating relays. So, as I mentioned, we used AccuSense voltage sensor, which is our product, using capacitive technology, because the goal was to measure the super harmonics up to 150 kilohertz. On the chart, you can see why we decided for the capacitive technology itself. So we can see the behavior of the resistive versus capacitive dividers, and you can realize that there is significant gap in the frequency response between resistive voltage dividers and capacitive voltage dividers. Plus, as you already know, we are using the active approach. So on the right side, you can see in the chart that the accuracy is not influenced by the frequency almost at all. Here we have 7 test scenarios which we performed. By the way, this test is available also as a white paper too, so you can write me an email and I can give you more details. So the scenarios were following. You have scenario number 1, 2, 3, 4, 5, 6, 7. their source, the test sequence description, and the time frame when, let's say, we start with each and every scenario. Most important for us are number 4, 6, and 7. Specifically, the islanding or DERs, then the solar inventors islanded and isolated, and then the last one is wind turbines islanded and isolated. So you can see also the test sequence here, and let's check the result. So as expected, power quality issues were observed. First one, voltage and frequency fluctuations. So as you can see on the first 3 charts from above starting, you can see a voltage fluctuations that were observed, probably luckily not exceeding 10%, but it was visible during DR's islanding mainly, causing drops down to 6.84 kilowatts. So we have nominal 7.2 line to ground. Same as the frequency deviations are visible in the bottom of the charts, where we have maximum difference of 0.6 Hz during the same conditions. Finally, another phenomenon is the supraharmonics. So as you can see on the chart, we observe them again during the DR's manipulation. So the maximum values were observed when the solar inverters and wind turbines were islanded, suggesting they are the main source of the medium voltage supraharmonic distortion. In the table, you can see the maximum values, what we measured with our AcuSense. So, for example, at 4 kilohertz, it was 4,000 volts, and it went up to 16 kilohertz, where we measured 500 volts. It's not everything. We also measured THD and flicker, so total harmonic distortion was observed in the level of 6.6%, so it is exceeding the limits that are given by ISIN IEEE standard, which allows maximally 5%. So we were above this value, and of course, you can see on the right side that flicker was observed too. You can see again, the timeline. So this phenomenon was again related to the DER's manipulation. What is the conclusion? So here we have like a summary of the mentioned scenarios 4, 6, and 7. So these are the observations. So when we were islanding all the DERs, we, let's say, saw the voltage drop to 6.9. We measured the supraharmonic frequencies up to 12 kilohertz. We also seen a flicker. In case of the test scenario number 6, where solar emitters were islanded and isolated, we saw some variation and instability in voltage magnitude. The voltage also dropped. The supraharmonics were presented at 14 kilohertz, and also the 2 frequency fluctuations and observations up to 60.5 hertz were observed. Scenario number 7, wind turbines islanded and isolated. Again, the voltage dropped. The supraharmonics were presented, and there was 1 frequency observation up to 60.6 hertz. So the whole event then, you can see that voltage sex at 5.76 kilovolt, and the frequency observation was at 60.3 hertz. Total harmonic distortion again with a flicker, and the supraharmonic frequencies were presented up to 24 kilohertz. So what is the conclusion of this test, of this real, let's say, test? So the AcuSense sensors helps us to prove that the DRs are, let's say, DRs are the one causing the power quality issues, all the phenomena that we just listed, as a supraharmonics, voltage instability, harmonic distortion, and flicker. Also, the DRs have an impact on grid power quality, and they are probably the main cause of the supraharmonics frequencies. The point is that it is there. We just need to understand. We just need to measure and to do some correction. But with the traditional instrument transformers, probably thanks to the frequency cutoff, we are not able to detect or to measure superharmonics. And you can see that we measured that from 4 kilohertz to 24 kilohertz. So it may be limited or undetectable with traditional measurement system, VTs and CT. So this is the reason why the high accuracy measurement is required, and you can see it on real use case. So from my side, this is everything. Thank you for your time. I hope you enjoyed the presentation. If you want to discuss more in detail some use cases or sensor portfolio applications, you can reach me out. My email is on the screen. And thank you again. And now it's time for the questions.
Well, thank you so much, Michael, for the very insightful and informative presentations. We now like to invite our audience to submit your questions through the chat box, and we'll do our best to address as many as we can along the way. But Michael, we have a question from the audience. Is it possible to connect high accuracy sensors to existing older IEDs that currently use standard voltage transformers? Can you explain how this integration works?
Okay, thank you for the question. This is possible. We have a solution with an amplifier, which allows you to, let's say, increase the output of the voltage sensor to the same levels which are expected from the conventional voltage transformers. So yes, it is possible.
Great. We have another question also. Our audience is curious to know, does G&W offer solutions for SF6 free switch gears?
Yes, we do. I have to say this is quite a hot topic these days. And we are already testing the GIS portfolio, what we have, specifically the smart bushings, to be compatible with the new types of gases, which can be used as a replacement of SF6 and with different pressures, and we are using it with different switchgear manufacturers.
Thank you. Next, we have a multi-part question here. Is it possible to connect more than one relay to the same sensor to handle various functions such as protection, power quality monitoring, and metering, and including revenue metering?
Okay. So in case of the active version, the RJ45 splitter should be enough. In case of a passive sensor, I think we should use a merging unit together with an amplifier. But it always depends on the application. Same as the revenue metering, it is more or less question for the application and for the IED, how they can adapt the signal.
Thank you. Another question is, are there specific protection relays or IEDs that work with these sensors? And what types of devices would you recommend?
Okay, I think I already mentioned that we don't want to focus on one IED manufacturer, and we are trying to, let's say, extend the list every year to cover all customer requirements. At this moment, we can say we are compatible with majority of the market and of the application, but the list is growing every year thanks to our R&D and our laboratory.
Michael, someone else is asking, from a customer's perspective, what are the main differences between resistive and capacitive sensor technologies? Could you highlight some key distinction in their applications?
So I think that from the customer perspective, so the biggest difference probably will be in the frequency range, as we have seen during the use case. So it's possible that the resistive will not be, let's say, supposed to sense the same frequency level as the capacitive technology. So probably yes, maybe some limited vision for the supraharmonics for the resistive sensor. So capacitive for the power quality is better.
Thank you. We do have time for our last question. Last question is, does the accuracy change with frequency?
Generally, the accuracy does not vary based on the frequency for the active sensors. Specifically, again, for the power quality measurement, where the frequency accuracy over frequency range is required. In case of the passive, again, the calibration factors are different based on the frequency. But okay, so again, here is, let's say, the advantage of the active sensors, so the frequency response. But in general, something must be, or this is something what needs to be set in the protection relay again.
Thank you so much for the answers again, Michael, and for the presentation. If we did not get to your question today, we will be sure to follow up after the webinar. Remember, ladies and gentlemen, the conversation does not end here, because in just 2 weeks' time, we will be hosting our flagship event, Enlit Asia, that will be taking place from the 8th to 10th October in KL, Malaysia. We invite you to join us in Malaysia together with energy professionals from across the region to explore the latest innovations, trends, and solutions in enabling a multi-dimensional energy transition. Thank you once again for joining us today. Thank you once again, Michael, for being here with us today. We hope you found this session valuable and look forward to continuing this conversation at Enlit Asia. Have a wonderful day ahead.
Have a great day.